application. So that's why we are interested in the higher dimensional field theories. So today I'm interested in an index called Witten index, which counts the spectrum of the BPS state in 5D or 6D supersymmetric gauge theories. So this is the definition of this index. It looks a bit complicated, but yeah, geometrically it's related to so-called Gopak-Kumar buffer invariant, which so Professor Kim already explained this invariant. So I'm not adding more word on this invariant, but this Gopak-Kumar buffer invariant is precisely almost same as this Witten index, or as an index they are the same, but as a partition function they are slightly different. But anyway, so in 5D gauge theory, this index agrees with the Nekrasov's instant partition function, and in 6 dimensions, it computes the elliptic genus of the self-deal strings or little strings. Okay, so in this talk, I'll talk about a very systematic and powerful approach to computing this BPS spectrum for any 5D and 6D theories. So I'd like to emphasize the word any here. So it means we can compute the moduli space of the holomorphic curves in the any local Calabi-Yau report. So this method is very powerful. But here I will assume that any UV finite 5D and 6D theories have either gauge theory description in 5D or in 6D on a circle computation, or geometric description as a local elliptic or non-elliptic Calabi-Yau report. So under this assumption, I will explain a very easy way to evaluate the BPS spectrum of this theory. By the way, this is totally physics talk, so I apologize that I don't know. I know very few of mathematics, so please understand. So this is my plan. So I first explain the dynamics on the Coulomb branch in 5D and 6D field theories. And then I'll introduce the Blowup formalism, which was basically developed by Nakajima here, Nakajima-san here 3 years ago. And I will show you how to generalize his approach such that it can be applied to generic 5D and 6D theories or any local Calabi-Yau report. And if I have enough time, then I will also explain the Blowup equations for 6-dimensional little string theories. But if I don't have enough time, then I'll skip this part. Okay, let me first introduce Coulomb branch physics of 5D supersymmetric gauge theories. So in 5 dimensions, we can have gauge theory description for non-trivial theories which have non-trivial UV shear, the fixed point. They preserve the H supercharges, and we have SU to R symmetry. And the theory consists of the vector multiplets containing the gauge field A mu and scalar field phi and ferromagnetic partners, and also hypermultiplets containing two complex scalar field. And this theory has a Coulomb branch, which is real dimensional, parameterized by real parameter phi, or vacuum expectation value of the scalar field phi in the vector multiplet. And at low energy on the Coulomb branch, the effective theory is essentially the abelian gauge theory, but their interaction is characterized by topological terms, so-called prepotential. And this prepotential for the given gauge theory data together with the metal content, you can quite easily compute this prepotential. So if you look at this form, then everything is determined by the group theoretic information and also the representations. Anyway, this prepotential encode many informations, almost all the information about the low energy physics. For example, the metric on the Coulomb branch is determined by the second derivative of this prepotential with respect to the dynamical caloparameters phi. And also cubic Chern-Simons term can be determined by the third derivative. So topological terms, which governs the physics and the low energy theory, is computed out of this prepotential information. So for example, SU2 gauge theory without any hypermultiplet would be one of the simplest theory you can consider. In this case, by using the information about this SU to gauge symmetry, you can precisely compute this prepotential. And out of this prepotential, you can compute the the cubic Chern-Simons coefficient, which is 8 for 555, and also cubic Chern-Simons terms for the M. M is essentially the mass parameter for the U1 topological symmetry, and this cubic prepotential can be evaluated in this way. And also in low energy physics, we have additional topological data, so-called mixed Chern-Simons terms on the Coulomb branch. We have two different types of mixed Chern-Simons term. One is the gauge gravitational Chern-Simons term, which is given by this. Again, this Chern-Simons coefficient is given by the information about the gauge algebra and the method representations. And also gauge asymmetric Chern-Simons terms can be evaluated in this way. So all these topological terms in the low energy theory can be evaluated easily from the defining data of these 5D gauge theories. So for example, SU to gauge theory, this gravitational and gauge mixed Chern-Simons term is -4, and asymmetric gauge mixed Chern-Simons coefficient is 2, and so on.
What is P1T?
Sorry?
What is P1T?
P1T is the first contract class. Yeah. So this is 5-dimensional theory. So you can consider the contract class on the 4 directions. And C2 is the second class. The asymmetry. Okay, so we are interested in the partition function on the omega background, which is almost equivalent to the Witten index I defined, except this prefactor. So the full partition function on this omega background is given by the product of this prefactor and the Gibbs invariant part. Okay. But this prefactor is completely determined by the topological data which I introduced, the prepotential and mixed Chern-Simons terms. And we are saying that we are claiming that this this prefactor is essentially the effective prepotential evaluated on the omega background. So by knowing this prepotential and the Chern-Simons coefficient, you can precisely determine this prefactor. And this prefactor will later become one of the most important input to formulate the Blowup equation and solve the BPSS pattern. But here the important message is that using Chern-Simons coefficient or the topological numbers, which I will explain in the Calabi-Yau threefold later, using this data, you can uniquely fix this effective prepotential and formulate the Blowup equation, which I will explain soon. So such 5D series or also 6D series compactified on a circle can be engineered in 11-dimensional M theory compactified on the local Calabi-Yau threefold. For 5D theory, it's just local threefold. For 6D theory, it should be the elliptically or genus one vibration, genus one fiber Calabi-Yau threefold. Anyway, the topological data in the field theory or gauge theory related to the topological data in the geometry of the Calabi-Yau threefold. For example, the cubic Chern-Simons coefficient is nothing but the triple intersection numbers of the divisors. For example, the simplistic example is the F0. F0 means the Hertzberg surface, which is embedded in the threefold. Then it provides the rank 1 theory, having the 1 dynamical parameters. In that case, the triple intersection number of this divisor D1 in Hertzberg surface is simply given by N. And this geometry actually engineers the SU to gauge theory 5 dimensions without any hypermultiplex, which I explained in the previous slide. And also other Chern-Simons coefficients are related to the intersection numbers. For example, the mixed gauge gravitational Chern-Simons coefficient is nothing but the intersection of the divisor Di with the second Chern class of the Calabi-Yau 3. So if you consider local P2 theory embedded in the Calabi-Yau 3, then this gauge gravitational Chern-Simons coefficient is nothing but -6. And also for the B blocks of the Hertzberg surface case, this number is -4 plus 2b. Okay, so the message here is again for the given any local Calabi-Yau threefold. If we know the surface is embedded in the local Calabi-Yau threefold, you can quite easily compute all these topological numbers that determines the Blowup equation. One missing ingredient in the geometry is this coefficient. This is mixed gauge and asymmetry Chern-Simons coefficient. As far as I know, this coefficient hasn't been discussed in geometry manner. But I'm claiming from the gauge theory study, this number is always 2 for any component surfaces in the Calabi-Yau report. So by knowing these intersection numbers or the topological data, you can evaluate the prefactor, which is curly E in this partition function. Okay, so last theory is the 60 SCFDs compacted by the circle. In this case, effective prepotential on the tensor branch or the Coulomb branch, the circle compactification, contains the one contribution from the KK mode, Kalasha-Klein mode, which takes exactly the same form as the prepotential I explained in the 5D gauge theory. But in 60 SCFDs, we have one more term, so-called the Green-Schwarz contribution, coming from the Green-Schwarz term. So Green-Schwarz contribution is needed in 6 dimensions to cancel the gauge anomalies. So they provide additional terms in the trilateral action like this, but this one provides additional contribution to the effective prepotential. So we should take into account this contribution to evaluate the prefactor in the partition function. And geometrically, these theories are realized by local elliptically fibered Calabi-Yau report. Okay, so let me now explain the Blowup formulation. So we will consider 5 equalities on S1 times C2, and we will blow up the origin of C2 by replacing it by the 2 sphere like this. Okay, and we will turn on the background omega parameters in this theory and evaluate the partition function using localization. And Nakajima-san and his friend actually computed this partition function for pure 4D and 5D SUN gauge theories. And they found that this partition function is actually factorized because under the localization, the fixed point, north pole and south pole become the fixed point of the Lorentz rotations. Therefore, under the localizations, the older computation reduced to the fixed point contributions. And furthermore, we can turn on the non-trivial magnetic flux for the gauge symmetry and also flavor symmetry on this P1. So the full partition function on this blow background will be given in this expression. Okay, we have sum over dynamical magnetic flux N for the dynamical gauge symmetry, and at each flux sector, the partition function is factorized into north pole contribution and south pole contribution. So this is the result of the localization. And furthermore, if we zoom in the geometry around these poles, south pole and north pole, the geometry is precisely the C2 geometry with shifted omega deformation parameters. So it means that the local contribution at fixed point is simply given by the C2 partition function with some parameter shifted. So in this way, so north pole contribution can be written in terms of the C2 partition function, or S1 times C2 partition function with some parameter shifted in this way. And south pole contribution is again given by C2 partition functions. Okay. So here N is the magnetic flux for the dynamical gauge field, and B is the magnetic flux for the flavor symmetry and so on. So we know how to compute this partition function on flow background, and then what can we do with this background or this partition function? Now we will blow down the P1 to point. Then our background will reduce to the original sheet background. And furthermore, this partition function turned out to be independent of the Kähler parameter for this P1. So volume of P1, this partition function is independent of it. So it means under this smooth transition, which blow down this P1, the partition function on blow background will reduce to the partition function on C2 up to some constant vector lambda. Lambda is constant. Okay, so we have now this non-trivial functional relation between the partition function on C2 and partition function on blow C2. And this non-trivial functional relation provides us a new method to evaluate this partition function on C2. As I said, this North Pole and South Pole contributions each can be expressed as the partition function on C2. So on the left-hand side, we have product of sheet partition functions, and right-hand side, we have the sheet partition function. And by using this relation, we can evaluate this sheet partition function iteratively. I will explain it soon. By the way, this relation has been studied in various different groups. Firstly, by Nakajima and Yoshioka and Goche, and the other groups here studied this relation for the exceptional gauge groups. And here, Shin studied the elliptic generalization and also the local Calabi threefold and their partition function in terms of the Blowup equations. And also you can introduce non-trivial defect operators such as Wilson loops and formulate the Blowup equations. So there are so many generalizations. And now I need to explain the magnetic flux quantizations. So magnetic flux can be turned on the P1 at the origin, and the flux must be properly quantized. And in this paper, actually, by using geometric argument, they proposed one interesting flux quantization conditions. It's the following. So magnetic flux coupled to the BPS state or the curve class CI with the spin JL, JR should be quantized in this way. So if 2 times JL plus JR is R, then this flux must be integral. Otherwise, it must be half integral. So this is the geometric flux quantization conditions. But we claim that this quantization condition must hold for all the cases. For example, for the cases without having any geometric realization. So in gauge theory, this means double boson should couple to the integral magnetic flux, but on the other hand, the hypermultiplex should couple to the half integral fluxes. So using this flux quantization condition, you can determine the magnetic flux for the gauge symmetry and also flavor symmetries like this. Okay, so this is the formulation of the formalism for any 5D and 6D gauge theories and also any local Calabi threefold. Now let me explain how to solve these Blowup equations to determine the Bopakuma-Baffa invariant. So to bootstrap this BPS spectrum or Bopakuma-Baffa invariant, we first expand this Blowup equation, both sides, in terms of the Kähler parameters. So Kähler parameter means the volume of these curve classes in the geometry, and iteratively we will solve it to determine this Bopakuma-Baffa invariant. And this expansion is well defined for any UV completable QFTs because they have the Coulomb branch where the volume of these curve classes in geometry are always non-negative. So actually you can make these are all positive so that this expansion is well defined. So after expanding the both sides in this Blowup equation, you can determine this Bopakuma-Baffa invariant or the y-order in this expansion. But there are 2 inputs, or they provide the initial data for this iteration process to evaluate the Bopakuma-Baffa invariant. One ingredient is the effective prepotential, and I explained how to compute it for any series. And also the other information is magnetic fluxes. So once you identify these 2 informations, so you can iteratively compute all the GB invariant. Okay. So this method is very powerful. So let me give you one concrete example. So we can consider 5D SU2 gauge theory without any methods. They are realized, so we have 2 different SU2 gauge theories depending on their set angles. One is a set angle 0, the other one is a set angle pi, and they both have geometric realization. One is realized by Hertzsprung surface F0 embedded in the Calabi threefold, and the other one is realized by Hertzsprung surface F1. And here this 2 phi and phi plus m correspond to the volumes of the 2 primitive curves in F0. For example, fiber class and base classes, they have the volume 2 phi and phi plus 1 for F0. And F1 has a different base class. And base class has a different mass or different volume, which is given by phi plus m. Okay, so they are distinguished. So fibers are the same, but they are distinguished by properties of this base term. But perturbatively, they are indistinguishable. For example, you can compute the pre-potential for these two series by using geometry or the gauge theory information, and pre-potential for these two series are given in this way. So they have the same pre-potential. So one input to the Blowup equation are the same for these two series. Furthermore, they have the same perturbative spectrum. So it seems that they provide the same Blowup equation. The question is, they both have, they each have different GV invariant. The question is, what makes the difference between these two objects? Actually, the magnetic flux quantizations for these two series are different because of the instantonic state or the curve class associated also. These base curve classes have different properties. For example, the M2 brane wrapping this base curve in F0 provide vector multiplet. But on the other hand, M2 brane wrapping this curve in F1 provide a hypermultiplet. And as I said, magnetic flux quantizations coupled to the vector and hypermultiplets, they have different quantization conditions. That makes these two Blowup equations for two series different, okay? So for example, SU2 theta 0 theory have integral magnetic fluxes for these M parameters. Okay. On the other hand, the pi theory has half integral magnetic fluxes. Okay. So prepotential, both theories have the same quantities. On the other hand, the magnetic flux quantizations are different. So if we solve the Blowup equation by using these inputs, then you get a different or distinct GV invariant. So we will expand the Blowup equation first in terms of this scalar parameter n. N is the one non-dynamical scalar parameter in the geometry. That at the first order in physics, in one instanton level, Blowup equation can be written in this way. So it's a linear equation in terms of three unknown functions. One is just the usual partition function, one is north pole, and the other one is a south partition function. Okay, so if we know, okay, if we have three independent, because we have three unknowns, and so if we have three independent Blowup equations, we can solve this equation to determine the partition functions or the spectrum or the GV invariant. Yeah, fortunately, we have more than three non-trivial magnetic fluxes, so we can solve it, and these two are the solutions to the Blowup equations at first order in this mass parameter expansion. And indeed, they have different spectrum, so they have different GV invariant. And actually, you can expand this Blowup equation further to higher instantons and determine all the partition functions. So in this way, you can evaluate the GV invariant. So here, there is one more comment. Here we used three independent magnetic fluxes or background magnetic fluxes to determine G and G north and G south. But actually, if we further expand this Blowup equation also in terms of the dynamical scalar parameters, you need only one independent magnetic fluxes or background magnetic fluxes. That is enough to determine all the GV invariant. Okay. Actually, using these Blowup equations, we computed the BPS spectrum for all rank 1 and rank 2 5D KK series and associated geometry. Rank here means we have the one dynamical parameters or two dynamical parameters. So rank means a number of dynamical parameters. So it involved the SU2 gauge theory with 8 flavors called E-strings, and at rank 1, SU2 gauge theory with one other joint hypermultiplets with the set angle pi and 0, and also all rank 2 series. For rank 2, we have 10 rank 2 series, KK series, and we can evaluate the BPS spectrum for all these KK series. Actually, once you compute the spectrum of KK series, you can compute the associated 5D CFT spectrums by using the RG flows. So this means for any rank 1 and rank 2, 5D and 6D series, we can evaluate the BPS spectrum by solving the Blowup equations. that involve geometrically all rank 1 and rank 2 shrink-up Calabi-Yau threefold, including all the Delpech surfaces. So this method is very powerful. So yeah, we are not missing any theory at rank 1 and rank 2. We can evaluate the spectrum of all these theories. And also it includes the new rank 1 SCFT, which is realized by this brain web with O7+. And geometrically, roughly, it's realized by Calabi-Yau threefold, embedding Delpech 2 with 2 exceptional curves identified. Okay. So this method is very powerful. Any question? This one?
Yeah.
Yeah, so Delpech 2 means you have 2 exceptional curves, right? You have 2 blobs, and you glue 2 exceptional curves each other. Then it will realize this geometry. This is not smooth geometry, and no one has studied, actually.
You said you embedded
Inside Calabi-Yau. Yeah. That embedding is not well defined so far. But our computation and also physics implies that such a geometry must exist. And without using any geometric data, we can evaluate the Gibber invariant of this geometry.
What's the flavor symmetry?
Flavor symmetry of this one. Yeah. This theory? Yeah. Yeah, this theory has SU2 flavor symmetry. Yeah.
So this one is KT or this one?
No, this is CFT. Yeah, as I said, this is CFT. So this is a new rank 1 CFT, apart from the CFT realized by Delpech surfaces. So as I heard from some mathematicians, the definition of the Delpech surface is the shrinkable geometry, which is smooth, and rank 1. But at rank 1, we have additional shrinkable geometry, which is not smooth, but realized in different ways.
Notation.
This notation means they are glued together. X1 and X2, 2 blobs in DP2 are glued together.
Why is now
Huh?
Why is now supposed?
Because of this gluing provides some, I forgot, nodal singularity or something. And maybe we can ask it to some geometries. Sorry? Curve. Cyber-Witten curve can be obtained by using the data about the BPS spectra. Actually, we have Cyber-Witten curve for this.
Studying the singularities. Study the singularity structure.
Yeah. What do you want to understand?
This one
SU2 flavor symmetry. Yeah. Yeah.
so that every there will be 5 singularities.
5 flavors,
5 singularities.
5 singularities. I have identified the singularity structure for that point. But the symmetry is identified by just looking at the spectrum, should be invariant. And also we computed the supercompile index. And supercompile index shows the SU2 flavor symmetry. Okay? Good, yeah. Okay, so yeah, for the last 10 minutes, I will explain the Blowup equations for 6-dimensional little string theories. So little string theories are not field theory, but they are non-local theories with the two-form tensor field, gauge field, and methods decoupled from the gravity. And one interesting feature of little string theories is that the intersection form of the tensor field is negative semi-definite. So it always have a single null direction, and the strings along this null direction, its tension defines intrinsic scale of this little string theories proportional to this m square. And furthermore, this little string theory enjoys interesting duality, so-called duality, T-duality. If we compactify this theory on a circle, then you can define winding mode and also momentum state.
What if it like this intersection form of the tensor field?
Yeah, so maybe it's better to explain geometrically. So you can consider elliptic fibration over some base 4 manifold. On base 4 manifold, you have holographic curves. This intersection form is the intersection of these holographic curves. Each holographic curve defines a tensor field. So null direction means so it has a zero eigenvalue always, or single zero eigenvalue. So the structure, yeah.
What kind of tensor field is that curve?
What is your
So this intersection form is the intersection form of curve.
Yes.
So when you say tensor field, what do you mean by that?
So F-shell construction is related to the type 2B with the Kähler base. Then in type 2B theory, we have D3 branes. That is a 4-dimensional object. And if we wrap this D3 brane on a curve, then the remaining 2 directions define 2-form tensor field. Yes. So T-duality for this winding and momentum state actually exchange this winding and momentum state in the other shell. So we have one theory with momentum and winding, and the other theory with winding and momentum, T-duality related these two theories. For example, 2,0 affine A1 little string theory has 2 curves on the base, forming the affine A1 algebra. And the other little string theory is 1,1 theory with SU2 gauge algebra. It has a base, on the base we have the fiber class. And this T-duality exchanges these two theories on the exchanging winding and momentum state. So this is quite interesting duality that characterize the little string theories. And associated Calabi threefold has 2 independent elliptic curve classes corresponding to winding and momentum states. So for example, this is the 2,0 A1 little string theory or 1,1 SU2 gauge theory. So it has one elliptic curve class labeled by tau and another elliptic class labeled by omega. T-duality is nothing but the rotating this diagram by 90 degrees. Okay. And another interesting feature of little string theory is actually it has mixed gauge global anomalies that are not cancelled by conventional or standard Green-Schwarz mechanism. So you have gauge anomaly in the presence of the background global symmetries. Okay. And to cancel the ABJ anomaly coming from this uncancelled anomaly polynomial, you need to introduce some 2-form field. And this introduction of the 2-form gauge, 2-form background field provide the 2-group symmetry. So under the gauge symmetry transformation for the 0-form symmetry, you need shift the 2-form gauge field. So this form 2-group symmetries. And this mixed anomaly again implies that broken global symmetries in the presence of the background gauge field for the symmetry. But to compute the partition function on omega deformation, omega deformed C2, we need to turn on the background field for the flavor symmetry and also Lorentz symmetry. So Mi is the background field for the flavor symmetry, so 1, 2 are the omega deformation parameters. But because of this mixed gauge global symmetry anomaly, which is not cancelled, we cannot turn on this background because it will break the gauge symmetry otherwise. Then how to compute or how to define the partition function on omega background is one important question to define the partition function in little string theory. And solution is like this. We can actually add some counter terms to the tree-level action. So there are so many ways to introduce counter terms, but we will propose the following counter term with auxiliary 2-form gauge field B0. So this counter term actually cancel the gauge anomaly in the presence of the background field by transforming this two-form auxiliary field in this way. And there is another proposal for this counter term in this paper, but we will claim this counter term is more relevant for the partition function of low background in this way. So if you have this counter term, the effective free potential receives additional contributions. And with this modified effective free potential, we claim that partition function of the little string series satisfy the following flow equations. And again, we can solve this flow equation to evaluate the BPS spectrum of the little string series or partition function of the little string series on omega deformed background. And here, the summation of this dynamical magnetic flux involve the magnetic fluxes for the auxiliary two-form field. So that is one crucial difference between the flow equation for the little string series and that of the usual 5D series. So let me give you one example. So little strings, the simplest little string theory is the theory living on the n parallel NS5 range in type 2 string theory. For example, 2,0 little string theory has a nice gauge theory description. So the little strings living in this theory has a nice ADHM high gauge theory descriptions. So you can compute the partition function of the strings in this theory by using ADHM construction, and this is the result. So this is the closed expression for the little string partition function when n is 2. So when the number of parallel NS5 range is 2, they correspond to geometrically this they correspond to this geometry embedded in the Calabi threefold. And we check that this partition function satisfies the following flow equation. But here, this little string theory has two tensors, but one tensor is non-dynamical. So it seems that we have just one dynamical flux summation. But since we added this counter term with the auxiliary two-form field, we need one more magnetic flux sum. So here, summation of the magnetic flux sum consists of the two independent magnetic fluxes. So this flow equation is satisfied by this little string partition function. And we did many checks for the other little string theories. So this flow equation makes sense for little string theories. Okay, let me conclude. So Blowup equations for the partition functions of generic 5D and 6D series on omega background can be formulated using two ingredients. One is effective free potential, and the other one is quantization of the magnetic fluxes. And using such Blowup equations, by solving it iteratively in caloparameter expansion, we can determine the BPS spectrum logically invariant. And for little string theories, we need to be careful about one more thing from the mixed gauge global anomalies. And once you add counter term to cancel such anomaly, you have extra contribution on the Blowup background. And to take into account such subtleties, you can formulate the Blowup equation and actually determine the BPS spectrum of little string theories. Okay, let me stop here. Thank you.